right, welcome back to Advanced Modeling Methods, and I'm going to leave this for a little later. Well, I'm going to start getting into MathCAD programming right off the bat here on lecture number 2, so that you get familiar with some easy codes. And you'll see how, for those of you who haven't tried MathCAD yet, you'll see how convenient and how easy it is to actually work on it. So this is Advanced Modeling Methods, and we are at lecture number 2. And so far we've actually looked at defining a method of weighted residuals, formulating it, and we started by doing so on a very simple problem, which is a heat transfer problem, a heat conduction problem in a 2D domain, general domain, with a domain omega and a contour or boundary gamma. And there's a generation. Some portion of the boundary was covered by first kind boundary conditions, so imposed temperature. Some portion of the boundary was covered by second kind boundary conditions, so imposed heat flux. And so we got to the formulation of the residuals. We said that there's a residual for the domain and a residual for each of these portions of the boundaries. All right. So what do we do with it? We said that there's, depending on the choice of the trial functions phi. Recall, we are trying a solution of the form and we named it T squiggle and we gave it the X and Y dependency, because we're restricting this for now to be a 2D problem. So we have a collection of coefficients multiplying trial functions. Remember that these trial functions are arbitrary, and it will just be a matter of determining these alphas, right, to find an approximation for the solution. So these alphas have to be found in such a way so that they minimize these residuals, okay? Alphas, the coefficients alpha j's, which are, there are n of them as you can see, are sought after in such a way that they minimize the defined residuals, or omega, or gamma t, and r gamma q. Okay? Now, in order to do this, a weighted sum of these residuals must be formulated. Such that, so what we have is the integral over the domain, which in this case is a double integral, right, because the domain is 2D. Omega, remember, being the domain of the domain residual, which is a function of x and y, times some weight function omega I of x and y, the omega, plus a contour integral over the contour gamma t over the piece of the boundary that is covered by temperature boundary condition of the residual gamma t that we defined last class times omega gamma t I. I'll explain all of these in a second. Plus an integral over the boundary gamma q of the residual gamma q of x and y times some selected weight function gamma q I d gamma must be equal to 0. Such that I goes from 1 all the way to n. All right, so this is what's called a weighted sum. It's integrated, and we're integrating over the domain. Remember, the whole problem is defined over a domain omega. One portion of the boundary is called gamma t, and the other portion of the boundary is called gamma q. Gamma t is where temperature is imposed, gamma q is what heat flux is imposed. Remember that for a problem to be well posed, no portion of the boundary, no portion of the boundary, or all portions of the boundary has to be covered by a boundary condition. Only one. We cannot have a portion of the boundary not covered by a boundary condition, or not imposed with the boundary condition, and we cannot have a portion of the boundary with two boundary conditions imposed to it. Okay? Temperature and heat flux. That will be an overdetermined problem that is solved completely different. But for a well-posed direct problem, these are the conditions. Okay? So we need, as you can see, I weight functions. I'm sorry, n weight functions. So we must also choose, not only we have to choose the trial functions phi for the approximation of the temperature, we also now have to select, somehow arbitrarily, some weight functions w, n number of them. Okay? So we now must choose n weight functions omega I of x and y. Well, some of them apply to the interior, some of them apply to the boundary, as you can see from this residual definition, whose form will dictate the minimization technique to be followed. All right, so let me stop for a second here and explain again what we're trying to accomplish here. I want to move these. All right. All right, so here's what we're trying to accomplish. Again, we set out to find some alphas so that when we multiply them, when we linearly combine them with some arbitrary trial functions phi, we find an approximate solution to the given problem. Why? Well, because either the given problem is not solvable analytically, okay, or we don't want to do it. We want to find a numerical solution, an approximation. Normally it would be because it's not available. It doesn't exist. It's too difficult to find or impossible to find because the geometry is not regular or for any of the other reasons that we already explained. Okay? So then we define some residuals. Remember this residual, and this residual we defined last week, which is basically the defect of that solution. That solution is not supposed to satisfy the governing equation exactly, and it might not be supposed to satisfy the boundary conditions exactly. It will satisfy them approximately. And that defect is embedded in here. This residual is basically how effective that approximation is in solving or satisfying the governing equation, okay, the differential equation. This residual is how effective that solution is in satisfying the boundary condition of temperature. This residual is how effective that solution is in satisfying the flux boundary condition. That's it. Now, it would be impossible to make these three residuals zero everywhere simultaneously, right? Because if we do so, we found the analytical, the exact solution. And that's impossible, or nearly impossible in most cases. So what we do is we try to get almost there. In order to get there, instead of setting them to zero, we try to minimize them. And a way to minimize effectively is setting up a weighted sum. Okay? I don't want to make these residuals exactly zero, but I want to make him zero in an average sense. Okay, what is an average sense? Well, an integral over the domain plus integrals over the boundary. Okay, so that would make those residuals nearly zero over the domain and over the boundaries. Now we have to decide what kind of weights do we use. We can use number one, okay? But we need n of them in order to find n alphas. Remember, the phis are arbitrary. We can pick, as long as they're linearly independent functions, we can pick whatever we want, okay? Then the alphas, we try to find. And in order to find them, well, we formulate this expression right here. We look for, or basically we arbitrarily select n weighting functions and carry out this integration n number of times with the different n functions to find the n alphas. So at the end, what's going to happen? We're going to end up with a square system of n equations with n unknowns. And guess what? Those n unknowns are going to be the n alphas. That's it. All right? Now, depending on the choice of w's, we're going to follow a different minimization technique. All right. So let's start with the first one. Co-location method. And remember, we're still within the framework of the method of weighted residuals. In the co-location method, the weight functions at the domain, or in the domain, those are selected to be the Dirac delta function at n points I equal 1 through n. Xi, so that I equals 1 through n. All right, so let's explain this. So the Dirac delta function, or the weight function, will be equal to Dirac delta function co-located at points xi, yi. And by the way, I failed to say that this was xi, yi. It's a point, and we're still talking about 2D. All right, so now we need to select n points somewhere in the domain. Right? And in those n points, basically we're going to collocate the Dirac delta function. Now, most of you don't know what a Dirac delta function is, but it's a very, very simple function that has very, very powerful properties. Okay? First of all, and this is the Dirac delta function. Let's define delta in 1D, to make it simple, right? In 1D, such that is delta of x comma xi. It's a function that has two arguments. X, which is a field variable, and xi, which is a collocation point, just a field point. I'm going to plot what this function looks like. This is x, this is y. Okay, we're talking about a 1D function. And this function is 0 everywhere. And then at xi, it shoots to infinity. It's called a unit impulse. And this goes to infinity. It's a unit impulse. All right. Now you can imagine that in 2D it's exactly the same. It's a function that is 0 everywhere, except at that location xi, in this case xi yi, where it would shoot straight to infinity. 0 everywhere, infinity, right at the collocation point, right at the location xi. How come a function that is 0 and infinite, we call it a unit impulse? Why unit? Where does a 1 come from?
It's integral.
It's integral, right? So, good deal. So it has the area property, which means that the integral from minus infinity to infinity of the delta function dx is equal to 1. Or, we can also state it as an integral between a and b is equal to zero if xi doesn't belong to ab, and 1 if xi belongs to ab. So if we integrate over x, and that range includes that collocation point, the integral is 1. All right, so we found a function whose area under the curve is 1. No big deal, because there's many functions like that. However, this one is a singular function. It's a function that is 0 everywhere and infinite at a point. All right. Yes.
Can you just explain the relationship one more time? So if the direct delta function from the integral from a to b, just run through that one more time.
All right, if we integrate the direct delta function, whatever the collocation of it is, okay, it's a function that depends on x only, but it has an argument xi, which is the point at which the impulse occurs.
Okay.
All right, if we integrate between infinity or minus infinity and infinity, the area is 1. Well, because the area under the curve only counts here because the curve only exists here. Everywhere else is 0. So we can shrink that area integral all the way to the vicinity of the impulse and still get 1, as long as the impulse is within a and b. That's what the second statement means. It's exactly the same. But I'm just saying that it applies not only when the limits of integration are infinity, but also when the limits of integration go from a to b. And this is a more reasonable form of the property because this is the one that we're going to use for numerical approximations. We never integrate between infinity and minus infinity. We use this one. All right. So again, it's a function. The Dirac delta function is a function that is, I'm going to use most of these, but it's not letting me. All right. The Dirac delta function is equal to 0 if x is different than xi, and tends to infinity, positive, if x tends to xi. That's the algebraic definition, that's the area definition. Now, you remember the Heaviside step function? The Heaviside step function, h of x comma xi, is a function that looks like this. This is x, this is y. It's a function that is 0 everywhere, and then all of a sudden jumps to 1. This is h of x comma xi. It jumps to 1 at xi. It turns out that the Dirac delta function of x comma xi is equal to the derivative with respect to x of the Heaviside function of x comma xi. It's a discontinuous function. This one is not a singular function, it's a discontinuous function. Okay? And as you can see, the derivative of the function is 0 everywhere because it's perfectly horizontal. The slope is 0, except at this location where the slope is infinity. So the Dirac delta function is exactly the derivative of the Heaviside function. Shifting property of the direct delta function. One property is such that the integral between a and b of f of x times Dirac delta function of x comma xi dx is equal to either 0 if xi is not in the interval from a to b, or is f evaluated at xi if x belongs to the interval a to b. And there's a really nice property. It's the only function in the world that does that. That does something like that. It eliminates an integral. If a Dirac delta function is inside an integral, the integral goes away. It's just the function that you're trying to integrate evaluated at the point of application of the unit impulse. So not only has an area of 1, that area of 1 means that if you multiply that function by any other function, function of x, and integrate it over a range, and that applies to 1D, 2D, or 3D. It really doesn't matter. Then the result of this integral is the function at the evaluation point, at the collocation point, as long as that collocation point belongs to the interval. Xi belongs to the interval from a to b. You see that? Is that okay? It's called the shifting because you're pretty much percolating the function f to the area of integration, or to the range of integration. You're shifting it, yes?
You're saying that the function will be 0 anywhere else but the collocation point.
Not the function, the result of that integral.
The result of the
Yeah, this function can be anything. You can pick whatever function you want, the most complicated function in the world. A function that doesn't have an integral. Remember when you were studying integrals in calculus 2, there are a lot of functions that cannot be integrated. Any function can be differentiated, however, that's not the other way around. Not every function can be integrated. There's not a closed form integral to any to all functions. You can pick whatever function you want, even the ones that cannot be integrated. And if there's a Dirac delta function inside the integrand, the result of this integral will be just the function evaluated at the collocation point. As long as the collocation point is part of the interval from a to b. If we make this minus infinity to infinity, this will always be the case. Okay, but then we're just going to limit the range of integration there.
So when we say collocation point, is that set value? Or
Yeah, it's an arbitrary location.
So like from 0, say our range is from 0 to 100, the collocation point is at 50. If
Well, we need to pick n of them, all right?
Okay.
Because remember, we need n weighting functions or weight functions to determine n alphas, all right? So you need to pick n Dirac delta functions. Where are you going to put the n Dirac delta functions? Well, you're going to put one here, one here, one here, one here, just to cover the entire domain. Think about a 1D domain from 0 to L. You're going to put one at 0, you're going to put another one at 0.1, another one at 0.2, another one until you cover the entire thing. You're going to put n collocation points. So you're putting n Dirac delta functions at n locations, and that is going to help you minimize your residual. How? We're going to see in a minute. All right? All right. So, an algebraic form of the Dirac delta function as part of these delta sequences is the following. The Dirac delta function from x comma xi is equal to the limit when k goes to 0, this is not x, this is k, of e to the x minus xi over k squared divided by k, I think it's k square root of 5, yes, k square root of 5. These particular algebraic form will satisfy all of these properties as long as k goes to 0. But as you can see, when k goes to 0, you have 0 over 0 in that expression. You have, that's a negative exponential. Yes, sorry, has to be. You have 0 over 0. If you have e to the minus infinity divided, which is 0, divided by k, so you have 0 over 0. But what grows faster, the numerator or the denominator? What goes faster to 0? This is an exponential square, so this one goes faster. And therefore, these actually, if you do L'Hopital rule, differentiate with respect to k, this will go to infinity at x equal to xi. Okay, and 0 everywhere else. All right, let's do a numerical proof that what I'm saying here is not wrong. All right, so I'm going to go to the computer and I've created the first MathCAD spreadsheet, and I've called it Lecture 02, which I'm going to post on Canvas. All right, so I've called it Dirac delta functions, just very simple. Actually, I can start from scratch just to see what am I doing here. I'm going to delete all of these. Let me delete all of these. And I put in a title there, it's just text, okay? How do you put text on MathCAD? Remember, MathCAD is a mathematical spreadsheet that is what you see is what you get. You can write your equations on the screen and get an answer right away, plot it right away. So, I'm even going to put the title. So, if you type something like direct, it's going to think it's part of an equation. See that blue underline? Think that direct is a variable name or the name of a function or something. As soon as you press the space bar, now it knows it's text, and notice it changes the font. Okay, so Dirac delta function. Okay, so I am going to underline it and all this, just to show that this is just the title. All right, so the first thing I'm going to do is define this delta, which is d. By the way, delta is Greek d, so to enter a Greek letter, I can just go to the Greek menu, just go to the toolbars and open the Greek menu, or just type d, Control G. Control G will give you access to all the Greek letters. So if you want alpha, you just type A, Control G. So you have alpha. Beta is B, Control G, so on and so forth. So D, Control G. I'm going to call it delta, which is a function of x, comma xi. All right. How do I write xi? I can write it like that, just xi, but if I want this to be a subscript, I can just say x point I. Point I will give me a subscript. It's not a subindex, it's just a subscript. Okay? Remember the difference between a subindex and a subscript? A subindex will be an index within an array, a vectorial array. I would just be, a point will just be a subscript. All right, and this is, move it down a little bit, and this is, in order to define something, you don't use equal, you use column. When you type column, it'll automatically bring the definition equal. Column equal, and this is the exponential function, so it's e to the power of. The power of is just shift 6, the control hat, of minus x minus xi, and this is divided by k, and this will be squared, and this is divided by k times the square root of pi. And what's the square root of pi? It's b control g. Right?
You say the P control G?
Mm-hmm. Pi is a Greek p. Now it's telling me that there's an error on this definition, and it's highlighting k. Well, k is not defined anywhere. So I can hardwire k. I can say k is equal to 0.1 or whatever. But when I want to show how this function looks like as a function of k, so what I'm going to do here is add another dependency to this function and call it k. Right? So I'm going to make this function a function of k so that I can see what it looks like. All right. So now I want to plot this function. I'm going to say xi. What am I going to call it? What am I going to say about the collocation point? I'm going to put the collocation point at 0. And the range, x, I want to go from -1 to 1. Okay? I'm going to plot this function between -1 and 1 with a collocation point at 0. So the function should look like it's pointing at x equals 0, pointing up. All right, so how do I define a range? Well, I want to go from -1. The next value in the range is a comma minus, let's say, 0.99, and then semicolon 1. That defines a range. The first, the second, and the last. Okay, the first separated by a comma, to the second separated by a semicolon. This is a semicolon. This is not 2 periods. A semicolon will introduce that to the last one. First, second, and last element in the range. Okay, so how many points are there going to be in this range? Well, 201. Okay? -1, 0.99, 0.98, so on and so on, all the way until 1. All right. So now I am going to insert. I know what the shortcuts are, but I can go insert, graph, and I want an XY plot. See? There's an XY plot. Let me zoom out a little bit. See better. All right, an XY plot. Another way of introducing an XY plot is just to stand here and say Shift 2. Shift 2 will introduce an XY plot. All right, so I want to plot. Let me make this a little bit bigger. Oh, not that big. This one out of whack.
I think we'll do everything.
No, it still scrolls.
Yeah. So Shift 2. Okay. Let me make this big. I can make it go horizontally. All right, so I'm going to make this X, and the x-axis, and on the y-axis I'm going to make a delta. That means D control G x comma x underscript or subscript I comma k, and k I'm going to pick a number. So let's pick 1 for k. Remember the definition says when that number k goes to 0. See? It's trying to do something. It looks more like an exponential, quadratic exponential function. It's supposed to be 0, then point up, and then go down. But it's not doing that. Alright? So I'm going to add, I'm going to make sure I select, when I pick something here, and see the cursor or blue underscript or underline is picking up that variable x, I can press the space bar until I select everything. And then press comma, and I can enter another variable there. And the other variable that I want to print is D control G, the delta function of x, comma x, I, comma, let's say 0.5. Let's say half of it. See how that blue line now is going up and it's getting skinnier. Do this again. Delta x, comma x, I, and let's say now 0.25. So now it's looking more and more. By the way, I can highlight this. Let me highlight just one. Control C, and I can Control V, cut and paste. And let me make this half of these. And let's do another one just for laugh. There we go. And the legend is automatically added, the colors and the line types automatically added, but you can change that. If you want to, you can double click on any of these traces. See, and you can select the type of color on each of the traces. You can select the line weight and the line type. Or you can put symbols, whatever you want to do. I can actually adjust the range. See, it's automatically, I described or I defined the range of x from -1 to 1. So it's kind of automatically adjusting the range of the plot, and it's doing it from -1 to 2 for some reason, but because it's automatic. But I can actually hardwire the range from 1 to -1. Now I can see the entire function. See that light blue is now staying very close to 0 everywhere except at the point 0. Now the ultimate test for these will be to integrate it, right? So if I say, I'm going to come back here and say, saving, I'm going to say k, and let's pick 1, right? Let's start with the number 1. And I'm going to say the integral, which is Control I, by the way, or I can just pick this one right here. I want an integral, oh, by the way, let's select an A and a B, a range of integration. And let's say we want to integrate between -2 and b equals to 2, right? We want to go outside this range, or even that. Let's just integrate between 1 and -1 and 1 to see what we get. By definition, a Dirac delta function should give you what? 1 for that integral, right? So if we integrate between a and b, we integrate the delta function x, comma xi, which is already defined, comma k, which I'm defining right here. By the way, MathCAD is a left to right, top to bottom interpreter. It's not a language, okay? You don't need to compile any of these. It's giving you solution as you go. It's parameterized, but it interprets what you write from left to right and from top to bottom. So if I do this, and I integrate with respect to x and say equal, now this is a regular equal, not the control equal, I get 0.843. That's not even close to 1. Okay? And obviously that's the case because I pick a value of k equal to 1. So if I were to put this k down here, it gives me an error. See? because it interprets from left to right, and since k is a line underneath this, it doesn't know what k is. It cannot solve that integral. All right, so I'm going to leave k here. All right, so if I make, move this here. If I make k, let's say 0.1, see that integral? It went to 1. Okay, so it's pretty accurate. And obviously, the smaller I make this number, the more accurate that integral will be. As a matter of fact, if I make it 0.1, it is telling me that it's 1 because probably it doesn't have enough display precision to show me the error. I can adjust the display precision by going here to the answer, double-clicking the answer, and say, I want to show maybe 8 decimal places. Oh, still didn't find it. 10 decimal places. Nope. Nope. Let's say 0.2. Wow, very accurate. There you go. You pick 0.5, the error is in the 3rd decimal place. So it's already getting pretty accurate to satisfying the area property, the unit impulse. Okay? Now, the real test will be the sifting property. Let's pick a very complicated function. Whatever you want, you tell me. F of x. Let's define a function that has everything you want. Polynomial, exponential, trigonometric. What do you want to do?
Sine x squared
Sine x squared.
times the cosine of
Okay.
e to the power
I'm going to tell you right now, sine x squared. What is the sine of x squared at x equal to 0? It's 0. The function is going to go to 0, right? So let's put something else in the parentheses and make them, because it's going to be easy for the. So let's make it plus 1. Okay, or plus I have. No, plus 1. Make it tough. Times what? Times the what? The cosine you said?
cosine of e time or to the power of x squared.
The cosine of e to the power of it?
Yeah.
Wow, okay. Alright. Something like that. Well, that's a nasty function. Alright, I guarantee you that you cannot get an answer to the integration of this function. It's impossible. Alright, now the integration by parts a million times will not get you there. But, if we somehow say, what is the integral, and I'm going to do this again, from a to b, I'm going to copy this here, and multiply this times f of x, dx, oop, see, I need to find it down here, 0.35. Now, how do I know, and let me put some trading zeros into this. I'm going to go all the way to 10. Okay, so what is the function evaluated at x side? To make sure that this is giving us the correct answer. It's not even close. This function evaluated at x side, which is 0, should give us 0.455. And this sifting property is giving us 0.3537. But I bet you if we make this number 0.1, the area property is still 1, and look at the sifting property, it's getting us there. Okay, even that nasty function is able to integrate, it's doing the full integral. MathCAD doesn't know that this Dirac delta function that we just defined up there has a sifting property. It doesn't know that it's supposed to transfer the value of the collocation point here to the evaluation of the function. It's actually doing that integral between -1 and 1. Okay, it's doing it numerically, internally. It's dividing the interval in trapezoids, like we do numerical integration, and it's arriving at that number. And if we do 0.01, we're getting there. Actually, I'm going to push this to the right. Maybe I overdid it here. Let's do 6 decimal places. Okay, and let's do 6 decimal places. See how close we are. There we go. 45, 46, 49. So we're almost getting there. I bet you again, if I go to 0.01, see? Oh, it's right there, we're on the nose. Okay? Now, we have to be careful because MathCAD is a numerical routine. Internally, it does everything through quadratures and trapezoids and things like that. So we might enter round off if we make this number too small. Mathematically, we can define a limit when k goes to 0, but numerically, 0 doesn't mean 0. You have to respect the machine precision and the round off of the machine. Okay? By default, MathCAD calculates everything and stores everything in double precision variables. Okay? You know what a double precision variable is? Internally, it uses 64 bits or 8 bytes to store all the trailing zeros in a scientific notation number, or the floating point number. Therefore, a 0 is, it has a precision of 10 to the minus 16. Okay? It can actually distinguish two numbers that differ by 10 to the minus 16 as two different numbers. So that's what's called the machine precision. So I can make this, I can even go, whoa, see? It cannot recognize that. See? That is already too small for the definition of the directed function. This one is already too small. That one did the job. Okay, so we gotta be careful when evaluating numerical expressions, not to get carried away by zeros or infinities. Okay, you have to make sure that it's satisfied. Okay, and when I tell you that the machine precision is about 10 to the minus 16, doesn't mean that you can make this number as low as 10 to the minus 16. You have to respect the floating point operations going on. Because remember, this number is embedded into a function that is being used in an exponential. It's being squared. So 10 to the minus 4 is being squared. That's already 10 to the minus 8. It's put into an exponential, which internally in the computer, an exponential is calculated as a sequence of addition and subtractions. Okay? An exponential is something very tedious for the computer to be able to calculate. It doesn't have an engine internally that tells it what an exponential of something is. It actually has an internal algorithm that approximates the value of an exponential as a summation sequence. That's it. The same thing for a division like this. So as you go to 10 to the 8 and divide by another 10 to the minus 4, you're already crossing the 10 to the minus 12 threshold. Okay? So that's why you're reaching machine precision as you make that number very small. All right, so that's besides the point. So this is where we're at. We define the directed the function, we define it numerically, we know what it does, everything seems fine. Our class is until 5 p.m. Oh wow, going slow. All right, so how does that come into play here? Let me go back to the document. All right. So, what do we do with these? Again, we define the directed of the function. We said that the weight functions in the interior, W omega, at x comma y will be equal to the direct delta function x comma y, xi comma yi. And I'm going to put a semicolon there to basically differentiate between the actual independent variable and where that direct delta function is being collocated. All right. So, we will formulate the collocation method or discollocation method as an interior method such that the boundary conditions are automatically satisfied. Therefore, the only remaining, put an extra A there, remaining residual to minimize is the domain or interior residual. That is, so we're back to the integral over the domain of the domain residual x comma y times omega, or weight function omega I of x comma y. The omega must be equal to 0. And therefore, the residual times the Dirac delta function is equal to 0. And if we apply the sifting property, what do we get? And therefore, omega of xi comma yi must be equal to 0 at I equals 1 to n. So this is the general definition of the residuals, only the interior one. The other ones we say are automatically satisfied. They all became 0. So if we make the weight function the Dirac delta function, then we use the sifting property, and it would just, this integral will disappear, will vanish. It would just basically be the evaluation of the residual at point xi, yi. Recall the residual and the domain, our omega, was the defect of the trial function in not satisfying the governing equation. The governing equation, remember, was the Laplace of t plus ug triple prime over k. We did this last week. This is the governing equation, right? The governing equation, if we use the exact solution, should give you 0. Because we're using the approximate solution, now you get something that is not 0 but is a residual. Something that you wish to make nearly 0. All right? Therefore, the Laplace of the approximate solution evaluated at xi yi plus ug triple prime over k must be equal to 0 at I equal 1 to n. So you select n locations, xi, yi, and order pairs, and evaluate this. And they all simultaneously must give you 0. All right. Now you remember this, right? This we defined last week. This was the governing equation, which is equal to 0. This is a equation that controls steady heat conduction with generation UG triple prime. K is the thermal conductivity of the medium. Now, because T is an approximate solution, you don't get exactly 0, but you get a residual. This collocation says that basically evaluating that residual at all these arbitrary locations xi, yi, make it 0, and you should simultaneously, if you do that, then you solve the problem. Not solve the problem, you approximate the problem. So how do we go from these to solving the problem? Let's see. Again. Okay, is it clear up to this point? And I haven't lost anybody, right? So again, recall that T hat is equal to the summation from j equal 1 to n of alpha j phi j of x and y. And remember that the phi j's are arbitrary functions. Wider, so I can see the 2 pages. All right, so I'm going to introduce this in this equation, and what do I get? Therefore, well, I'm going to say T of xi, yi is equal to the summation from j equal 1 to n of alpha j phi j of xi, yi. Now I have the trial functions, which are arbitrary, evaluated at arbitrary locations xi, yi. Introducing into minimized residual form, which is this function right here. Then I have Laplace of this whole thing, bracket this, from j equal 1 to n alpha j, ej, xi, yi, plus ug triple prime over k is equal to 0. Right? Now, the beauty of these, and any of the formulations of the method of weighted residuals, whatever trial functions we use, whatever weight functions we use, in this case we use the direct delta function as a weight function, they're always, the approximation is always a linear combination of coefficients and trial functions. These functions here can be nonlinear, can be whatever you want, can be exponentials, trigonometric, polynomials, whatever you want. They're arbitrary, but still a linear combination of these functions and the coefficients. And the only thing you need to determine are these coefficients. Once you determine these coefficients, the problem is solved. Okay? Now, because this is a linear combination, I can take this Laplace. The Laplace is being applied over a sum of alpha times functions, alpha times function, alpha times function, and I can pass them over to the function, because this is a constant, right? So I can say that this is equal to the summation from j equal 1 to n of alpha j times the Laplace of phi j evaluated at xi, yi is equal to minus ug triple prime over k. Again, such that I goes from 1 to n. All right, so I have some j's and I have some i's. The J there is indicating the coefficient. The I there is indicating the collocation point. J, the index J goes from 1 to n. The index I goes from 1 to n. So this looks like a square system to determine the alphas. Remember again, phis are arbitrary. So whatever arbitrary function or functions are selected as trial functions Vj of x and y, their Laplace, which is this, or forget about the I, is easily found. For instance, let's say, again for the sake of argument, phi1 of x and y is equal to 1. phi2 of x and y is equal to x. phi3 of x and y is equal to y. phi4 of x and y is equal to xy. X times y. Pages apart. This is a times. All right, let's continue here. Phi5 of x and y is equal to x squared.
Could you slide in the top page just a tad?
Yeah. Phi6. All right, let's stop there. Let's say that we pick 6 trial functions for these 2D problems. That's very little. So just for the sake of argument here, for the sake of example. All right. Remember the Laplace of phi of x and y is equal to the second derivative of phi with respect to x squared plus the second derivative of phi with respect to y squared. And therefore, the Laplace of phi1, okay, if phi1 is equal to 1, what is the Laplace of 1? Huh? If phi1 is equal to 1, right there, what is the second derivative of 1 with respect to x squared plus the second derivative of 1 with respect to y squared? Y squared. 0, right? It's a derivative of a constant. You get 0. What is the derivative? What is the Laplace of phi2? Given that phi2 is equal to x. What is the derivative of x with respect to x? 1. What is the second derivative of that with respect to x? 0. And what's the derivative of that with respect to y? 0. So it's partials, right? So it's all 0. Laplace of phi3 with respect to xy is equal to 0. Laplace of phi4 with respect to xy is equal to, well, phi4 is xy. This will also give you 0. Laplace of phi5, what is it? Given that phi5 is x squared, you get 2. So at least the last one that wasn't 0. And then the Laplace of phi6 is equal to 2. And then you can keep going. You can define more functions, and whatever you do, the Laplace is always easily found. All right? And the point is that whatever functions you define, then the resulting system will be, again, Laplace the summation of alpha j from j equal 1 to n phi j of xi yi is equal to minus ug triple prime over k. K being the thermal conductivity, not the k of the Dirac delta function, not to be confused. So here we have, again, alpha 1, phi 1, x1, y1, plus alpha 2, phi 2, x1, y1, plus alpha n, phi n, x1, y1 is equal to minus ug triple prime over k. That's when I is equal to 1. Again, remember this is for I equal 1 all the way to n. So when I is equal to 2, what do you have? Alpha 1, forgot the Laplace. Alpha n, x2, y2. And one more line before we leave. So alpha 1, Laplace of phi 1 evaluated at xn, yn, plus alpha 2, Laplace of phi 2, xn, yn, plus alpha n, phi n, to xn, yn is equal to minus ug triple prime over k. And as you can see, this is a system of n equations for n unknowns, square system of n equations for the n unknowns, alpha 1 all the way to alpha n. Problem solved. And that's it. So it is a matter of picking the trial functions, the collocation points, and the problem is solved. Obviously, you have to solve the square system. That's a matrix, a vector, and a right-hand side. Solve for the vector of unknowns, and you get your answer. Any questions? All right, so when we get back on Thursday, we're going to exercise this with a 1D problem, of which we know the exact solution, and see if we can approximate and how well we can approximate. All right?